Hello everybody, this is Iftikhar Ahmed back with my new video on optics. So today we will be talking about thin films. So in the previous classes we have studied interference due to division of wavefronts, and from now onwards, from this class onwards, we will be talking about interference due to division of amplitude. So the one of the application where we see the phenomenon of interference due to division of amplitude is in thin films. So the question is, what are thin films? So the thin film is an optical is an optical device, like it's uh, a thin, some kind of transparent material. It can be glass, it can be mica, any transparent sheet. And if you are calling it as a thin film, it has to have some some range of thickness, then only you will call it as thin film. And if you have a film whose thickness is more than that range of thickness, then you won't get an observable interference pattern due to that film. So if you want to get a interference pattern which can be observed easily and which can be easily viewed, that interference will come only in thin films. Okay, so what should be the width of the film so that we can call it as thin film? If it is a thin film, then only it will give you the interference phenomena. So let's see what is that range of thickness that a thin sheet should have to become a sheet should have to become a thin sheet. So if the thickness, this thing, of any transparent material, either glass or mica, any transparent material, if this thickness is coming around one wavelength, then you can call it as a thin film. One wavelength means what? If it depends on the electromagnetic spectrum, so the blue ray wavelength will be lesser and the red light wavelength will be higher. So that wavelength should be, that one lambda should be in the range of 0.5 micrometer to 10 micrometer. If any sheet is having its thickness from 0.5 micrometer to 10 micrometer, that sheet we can call it as thin sheet, and that sheet will give you a observable interference pattern with it. So we see these kind of interference phenomena in our daily life, in soap bubble, and the other example is on a plain road. If you drop some oil drops on the road, the oil drops will spread throughout the road, and those oil drops will form a thin layer of transparent sheet. The oil is a transparent material, we know that. So that transparent sheet will act like a thin film, and it became thin film now. So the when white light from the sun fall on it, that white light will undergo interference phenomena, and because of that interference phenomena, we see colors on a oil drop which got fall on the which is on the road. Okay, that is the reason why we see the fringes on the oil drop which is on the road. And the other application where we can see these phenomena is in the bubbles. You have in the soap bubble we see colors. So the soap bubble thickness is coming under this range. Its thickness is coming under this range. That's why that thin layer of the soap bubble, when the white light, any sunlight or light from the tube light fall on it, that light will undergo interference, and because of that interference you will see colors on the soap bubble or on the top of the soap bubble. That is the reason why we see the colors. So in physics, in nature, there are so many phenomena, so many beautiful phenomena undergoing, and we can give explanation for all those things with the help of physics. So today we will be talking about microscopically in detail how the white light is giving you the interference pattern with the help of a thin sheet. What is actually happening inside a thin sheet? What kind of physics we can apply there to find more interesting stuff about light? So let's get started with thin films. So now we will study how the thin films will work. So the thickness won't be this much large, but for our understanding purpose, I'm drawing it in a broad manner. So this is my thin film, glass material it is. Now, when when white light or when light source fall on it, the part of the light ray will get reflect back, and the part of it will get refracted. The part of the light will get transmitted. So this is the original direction, but because of the change of the medium, the light will suffer. There will be a bend towards the normal because the light is traveling from rarer to denser. Always remember, when the light travels from the rarer medium to the denser medium, the outcoming light will always bend towards the normal. This is the normal. We draw the normal to get the angle, to get the angle, at what angle we are incidenting light and at what angle the light is getting reflected. So this is the angle of reflection. You can call it as theta r. So this is the reflection. So the question is, so you have sent some light and the part of the light got reflected and the part of it got transmitted. So I want to know what fraction of light got transmitted and what fraction of light got reflected. We can get the answer for this question using the coefficient of reflection. I am denoting it with capital R. That coefficient of reflection will tell you what fraction of light will get reflected and what fraction of light will get transmitted, and that depends, the coefficient of reflection will depend on the medium's mu. The mu and this is the air, and here we have the glass. So glass mu and the air mu, they both combine and they will give you the value for this. So refractive index for the air to glass is 4%. 4% means what? If you are sending 100 light rays, 4 light rays will get reflect and 96 light rays will get transmit if you are incidenting light on a glass. That's why on a plain glass we see some reflection, and we because of that 4% of light we can see ourselves on completely transparent glass also. So that is the reason. Now the transmitted light will again suffer reflection from the bottom surface of the thin film, and part of this light will get transmitted. So this is the actual direction of it. But always remember, when the light travels from denser medium to a rarer medium, the light will bend away from the normal. This is the normal. The light will bend away from the normal. So actual path is this. So the light will bend away from the normal. So here we were having 96% of it. Out of this, from this coefficient of reflection, 3.8% of light rays will get reflect from the bottom surface of the thin film, and 92% of it will get transmit. And again the same phenomena, same thing will happen at the top surface of the thin film. Again from here, the part of this reflected light will get transmitted. So this is the actual direction of it, but it won't follow that because the light is traveling from denser to rarer. It will bend away from the normal. So this is the normal, it is bending away from the normal. So I am calling this ray as ray 1 and this ray as ray 2. Okay, so this is my ray 1 and this is my ray 2. And again the part of it, some part of it will get reflected, and similarly again reflection and transmission. So same thing this will happen. So because, so after this phenomena, after the occurrence of all this thing will happen within a fraction of second, because light is having a huge velocity, we know that. So what actually it is happening here is, there is some amplitude, the initial wave is having some amplitude, because the light rays got split up, part of it is getting reflection and part of it getting transmission. Because of that, the amplitude of the wave will decrease. If you sum them up, you'll get this thing only. But because they got split up, that's why the amplitude will divide. So that's why we are calling it as interference due to division of amplitude. Okay, so now again this reflected light ray will also have some amplitude with it. Okay, so now these two reflected light rays will have almost equal amplitude, almost all equal amplitude. Here's it is having 4% of light is getting reflected, and this light rays are 3.65%. So they almost have the same value. So that's why when these two rays meet, we will see interference pattern. So they are exactly parallel with each other. So how you gonna see the interference? Because if you want to have the interference, the light rays should merge. But from this geometry, what we are seeing is that they are exactly parallel to each other. So so this thing, they both are merging. Our eyeball is doing that thing. Our eyeball is a type of lens. When the light rays come, so that lens will merge these light rays, and we see the interference of these two light rays there. So I'm just showing you the two light rays. It is not just only two lights are doing it all. There are so many of them, but only for the understanding purpose, I'm taking example of just two light rays. Okay, so this thing, the parallel problem is taken care of by our eyeball, convex lens. So similarly, we will see exactly opposite. I won't talk about those things right now. We'll be discussing them in detail there, but with the help of these transmitted lights also, I'm calling it as T1 and T2, we will see the interference pattern due to this transmitted lights also, and we will see the interference pattern due to the reflected lights also. So this is how we see interference in thin films. Thank you so much for watching. In my next video, I'll be talking about interference due to the reflected light rays. So I'll be showing you how we can get the interference pattern due to these reflected lights. We'll be dealing with some mathematical stuff, what kind of math we will be using there, what is the condition for the bright fringe and what is the condition for dark fringe. We'll be dealing with all those things in my next video, so stay tuned.